session, we are going to discuss about the Class B power amplifier. Already we have told the Q point is located exactly on the x-axis. So if it is going to be placed on exactly on the x-axis, what happens in the sense, I could get only one half of the signal for both the collector current as well as the collector emitter junction voltage. I could get only one half cycle. Why? Because means if I'm going to extend this part, okay, if I'm going to draw a input waveform, what happens in the sense, if this is going to be our input waveform, I could get the conduction only during this time. Okay, at this time there is no conduction at all. Why? Because means the voltage level is falling below the zero. Okay, the biasing voltage is less than zero. Even if it is less than 0.7 volts at all, the device will not come into conduction. Okay, so only during only one half of your cycle only, we will be getting the output. Okay, so what we have to do in the sense, here we are going to make use of pair of transistors. Pair of transistors in the sense, I am going to make use of two transistors in case of your Class B operation. Okay, the way in which I am going to connect the two transistors differs. Okay, first one is push-pull Class B power amplifier. Okay, from the name push-pull in the itself, we could identify push is going to be something we are going to forcing inside, towards. Pulling means we are trying to move outwards. Okay, that is your push and pull. In both the cases, what we have to do in the sense, we are going to make use of same category of transistors. If one is NPN, the other is also NPN. If the one is PNP, the other transistor is also PNP transistor. Okay, they are connected in push-pull mode. The other one is going to be complementary symmetry. Complementary in the sense, what happens is exactly just opposite. Okay, all other things are going to be the matched parameter. Okay, but if this is going to be in the plus, we are going to get it in the minus value. Okay, that is the case of your complementary symmetric Class B power amplifier. Okay, one transistor will be NPN, the other will be PNP. Right? Now let us concentrate on your push-pull Class B power amplifier. Okay, I need the output for the entire cycle, not for a half cycle I should get the output. I need the output for the complete cycle. Okay, whether it is coming out for 360 degree or 180 degree or in between 180 degree and 360 degree or less than 180 degree, I never mind about that. We need the output for the entire complete cycle. Okay, the output should be present over there for the full cycle of the input. Okay, so that is the thing we need to convey here. Okay, so let us check how the transistors are being connected in Class B configuration. Okay, so here we are going to make use of a center tapped transformer. Okay, what is the speciality of center tapped transformer? Or else, have you used the center tapped transformer ever before? Okay, in the Class A power amplifier, we use the transformer, right? But in the transformer, we use the step-down transformer. Okay, the windings does not remain the same in case of a direct coupled Class A power amplifier. Clear? Now, I am just asking whether we have used center tapped transformer ever before. Yes or no? Any one answer I require from all those who are present here. Type at least yes or no. Whether we use center tapped transformer ever before. Right from your third semester till yesterday's class, we had come across the center tapped transformer or not. Yes. Are you all here? Those who are in the session, type yes. So without your interaction, it is very boring for me to take the topic. I need at least a very, very few answers. Whether we had seen the center tapped transformer, you are giving the attendance all right? Thank you. Whether we had seen center tapped transformer or not. This is the center tapped transformer. Am I right? What we have done in the center tapped transformer. Okay. So look at the case. Okay. I'm not going to ask you any difficult questions and all. Okay. If you have any doubt, please hold me there and ask me to repeat again. Okay. I won't pose questions. Okay. Right. So this is going to be a class B power amplifier. In this, I'm having two transistors Q1 and Q2. As already told, in a push-pull class B power amplifier, okay, one transistor will be pushing the network, the other will be pulling the network. If so, in how they are connected in the sense, right? So both here you can see both the transistors are connected in that is, I have taken both the transistor as NPN transistor alone. Okay, I have taken only the NPN transistor. In this particular diagram, we have taken Q1 and Q2 of matched characteristics. That is, right from its current drain, that is its base current, collector current, even all its physical attributes is going to remain the same. That's why we are saying this Q1 and Q2 as matched transistor. Okay. So all the parameters is going to remain the same. Only thing is, this is going to be in NPN connection. This is also in the NPN connection. Only thing, I have made the emitter connected. Okay. So the configuration alone we had changed. Okay. If Q1 remains in the common emitter configuration, okay, whereas this Q2 remains in your emitter follower connection. That is the only difference. I have changed only the configuration, right? These are connected through the emitter terminal, right? So this is the center tap. What happens here in the sense when I am going to apply the input as a AC sinusoidal waveform, okay, for the transistor Q1 base, we will be getting a positive signal. At the same moment, what happens? Here we will be getting a negative signal. This is generally in case of your transformer. Okay. Here, what happens here? If I am going to give a complete cycle, okay, let us consider only the positive half cycle. During the positive half cycle, your base terminal is positive, whereas the emitter terminal is negative. Your base is positive with respect to emitter. Similarly, for the same input, positive half cycle, in the Q2, what happens? Q2 will be positive. The emitter of Q2 will be positive and the base will be negative. Can you understand what I am saying? Okay, we have told both the transistor Q1 and Q2 are of identical characteristics. If they are going to be identical in the sense, only the terminals. For the first transistor, the emitter is negative, and for the second transistor, the emitter is positive. That is the only difference which makes this amplifier as a push-pull network. Okay. Upon applying a DC bias, what happens? This Q1 will be trying to push towards this collector, and this Q2 will be trying to move the entire circuit towards this particular collector terminal. Okay. This is the thing actually happens in your push-pull class B power amplifier. Right. You could see in the diagram itself. In the output also we are having the transformer coupled. In the class A power amplifier itself, we have discussed that compared to the direct coupled, the transformer coupled power amplifier output is feeble. Okay, so this is your transformer coupling to the next stages and all, right? So here what happens in the sense, the transformer TX1, that is will be acting as the input transformer, and this will function as the output transformer. Okay. The other name for this transformer is referred as phase shifter. Okay, this is referred as phase shifter. Why is it so? Here the emitter is negative, here the emitter is positive. That is, the inputs remains 180-degree out of phase. Here we are getting a positive signal alone. Here we are getting a negative signal alone. Okay, the inputs will be phase shifted by 180-degree. Okay, both these two signals with opposite polarity will be driving the transistor Q1 and Q2. During the positive half cycle, this transistor will be made on, this will be in the off state. Similarly, during the negative half cycle, this transistor Q2 will be on and Q2 will be remaining in the off state. Right? So, at any one particular half cycle, any one of the transistor will be in the conducting period. Clear? Right. What is the duty of this output transformer? It just couples the output that is coming through Q1 and Q2. That is, it just reminds us the adder network. It just adds the output of your Q1 transistor and Q2 transistor. Okay. Here Q1 is conducting during the positive half cycle and Q2 is conducting during the negative half cycle. As on a whole, we are getting the output for the entire complete cycle. Okay, that is our motto, right? We need complete conduction, right? Let us see the working of the transistor. Okay, initially what happens, the transistor Q1 and Q2 will be selected or biased in such a way both of them remain in the cutoff region. Okay, so how it could be happen in the sense, at both the base we are going to provide bias voltage less than 0.7 volts, that is less than your cut-in voltage. The bias is going to be present at the base terminal. Okay, therefore the same thing what we have explained here. Okay, so what happens during the DC operation? We don't have any AC input at all. We are going to apply only the DC signal, right? So for class B power amplifier, the Q point is on exactly on the x-axis. That is VCQ equal to VCC and ICQ is 0. Okay, so therefore how it could be happened in the sense, as I told already, we have made the base voltage of Q1 and Q2 always less than your cut-in voltage, so that both the transistor remains in the cutoff duration. Right? So we know that this is similar to your full wave rectifier. This is for the first half cycle, that is during your positive half cycle, and this is for your negative half cycle. You could see in this the figure. Okay, so during the positive half cycle, I1 is conducting, and during the negative half cycle, I could get the I2. If I combine them both, we will be getting twice Im by pi as our DC current. Clear? Right. We know the expression for DC power, that is equal to VCC into IDC. Okay. So also we know, kindly